Welcome to this lecture on the topic of electromagnetism. I think it goes without saying why it's important to study electromagnetism before we jump into topics that are solely associated with electric circuit analysis. So let's go ahead and jump right in. I'd like to begin by talking about some fundamental properties and values related to electromagnetism and the physics behind it. So let's discuss energy, entropy, and why we must spend energy to perform work. Because really, that's the objective of most electric circuits, to perform some practical task. Our universe began as a hot and uniform material packed into an infinitely small space. That's the Big Bang Theory. And it will most probably end as a cold, dark universe where energy exists, but is scattered in such a way that no work may be extracted from it. There's varying theories on exactly what will happen at that point, but let's just assume that expansion continues forever. The beginning, at the Big Bang, we have a universe that's highly ordered with lots of potential energy. We call this a low entropy state. And the end is highly disordered with no potential energy. We call this a high entropy state. I'm sure most of you know that the arrow of time of the universe is dictated really by the overall progression from low entropy to high entropy. And so here's a little picture just showing, right, we start off with the Big Bang. We have low entropy because energy flows from hotter to cooler areas. We can extract work from that. And then in the end, we have the big rip where photons and subatomic particles are evenly distributed. This is a high entropy state because there's really not any work that can be extracted from that energy. So naturally, I said this before, our universe becomes more and more disorganized. Entropy always increases on the largest scale. However, we can use energy to perform work and create order or reduce entropy on smaller scales. So we may not be able to return the entire universe to a more ordered state, but it's very possible to clean your room, let's put it that way. One example is taking pieces of a broken plate, which are disorganized, have a relatively high entropy state, and using our biological energy, right, our energy as a human, we can put it back together into a more organized or lower entropy state. And the ability to extract work from energy to reverse entropy on our planet is obviously important to our civilization. Again, without the ability to consume food, convert that into usable energy, and put our plate back together, there's really no way to achieve those types of tasks. So, we're going to generalize that to our electric physical system. So let's talk about some other ideas and concepts related to entropy and physics. Electromagnetism. The electromagnetic force describes the physical interaction between electrically charged particles. The force is carried by an electromagnetic field that is in turn composed of the electric and magnetic fields. Visible light, like radio and X-rays, hopefully you know that really those are all part of the same electromagnetic spectrum. The only difference between an X-ray and light that we see is the frequency. So visible light, like radio and X-rays, is part of the electromagnetic spectrum. And so here we see a picture of the electromagnetic spectrum, which ranges from very low frequency radio, microwaves, up into infrared, visible light, ultraviolet, X-rays, and then you have the highest frequency gamma rays. So electromagnetism is one of the four fundamental forces, along with the strong force, which describes the fundamental interaction between subatomic particles of matter, binding quarks together into protons and neutrons. We have the weak force, which describes the mechanism that facilitates radioactive decay, and gravity, which essentially makes apples fall on Isaac Newton's head. A little bit of a joke there, or a simplification, but hopefully you are all familiar with what gravity is. Now, electromagnetism is the fourth of those forces, right? We have strong, weak, gravity, and then electromagnetism. Electromagnetism is important both on macro and micro scales, with that force attracting an atomic nucleus to its orbiting electrons, which anyone who's taken chemistry understands how important that is to defining the way in which matter works and the way in which atoms form molecules. Okay, so now moving on to electric charge. Electricity describes a set of physical phenomena associated with the presence and movement of charges or charged particles. The presence of an electric charge, whether positive or negative, produces an electric field as shown below. So here we see some electrically charged particles sort of floating in the void here. These particles generate an electric field around them, and when two particles approach one another, we can see that there's a predictable interaction between those fields, which will lead other charges, let's say you have a charged particle, a positive charged particle here, will lead them towards their oppositely charged partners. The movement of electric charges, which we can call current, generates a magnetic field. I'm not going to spend as much time talking about magnetic fields here. It's a somewhat more complicated topic, and we're going to touch upon it later on in this class. But for the most part, what we see is that moving charges create magnetic fields and vice versa. Magnetic fields can also cause charges to move or can excite a current. Most of you are probably most familiar of this from physics class using the right hand rule, which demonstrated that if you look at the direction of in which your thumb is pointing, that represents the flow of a current. And then if you move I can't really demonstrate it here, but if you move your other four fingers in the appropriate direction, that would show the direction of the resulting magnetic field. So, when a charged particle, like an electron, is placed within an electric field, I think I said this a second ago, a force will act upon that charge, repelling it from like charges and attracting it to opposite charges. The magnitude of that force is defined by Coulomb's law, which is presented here. We see here that the attractive or repulsive force experienced by two particles by one another is calculated by the Coulomb's constant, which is defined down here. The charges of those two particles, these should be signed values because that would determine whether the force is positive or negative. And then the radius, or the distance between those two particles, squared. Down here you can see I demonstrate how the units of this calculation work out in order to yield a value in newtons. Essentially, right, this here is they are the units of the Coulomb's constant, and then here we have the units of the calculation, coulombs times coulombs over meter squared. These cancel out, leaving simply newtons, which is the unit we would expect for a force. Electric charge is a property that causes matter to experience a force when placed in an electromagnetic field. This is an inverted form of our previous statement. It's sort of self-referential, but that's okay because that's essentially the way in which we define electric charge. Electric charge can be positive or negative. Like charges repel and opposites attract. I think most of us are familiar with that phenomena. In ordinary matter, so we're not talking about antimatter, negative charge is carried by electrons, positive charge is carried by protons, and essentially if you have more protons than electrons, the net charge is positive, and if the opposite is the state, then you would have a negative charge. Charge is quantized, meaning that it can only change in discrete steps, whose minimum is the elementary charge of an electron. That's this value here. 1.602 times 10 to the negative 19 coulombs. Now normally we consider E to be a positive value, even though, right, the net charge of an electron would be negative. There is one exception to this, the quark, a subatomic particle, which we don't discuss in this class, and that has a charge of 1/3 E. The standard international unit of electric charge is the coulomb. We've been talking about it above, and it's described below. It's defined as the quantity of charge that passes through the cross-section of a conductor carrying 1 ampere for 1 second. So essentially, you have this cross-sectional area right here. If you know that the flow is 1 amp, then that essentially says you have 1 coulomb worth of charge that will pass through that cross-sectional area in 1 second. So the value of Coulomb is based off of the amp, but ultimately really based off of the charge of an electron. So I would say this is probably the most fundamental definition of the Coulomb, because, right, the charge of an electron is a physical constant. So I don't go over all the homework problems. This one I am going to talk about briefly. So we have two different charged particles. One has a value of positive 10e, the other one has a value of negative 20e. So already we can say that we expect those particles to attract one another. And then we have our Coulomb's constant right here. We want to use MATLAB in order to calculate and graph the attractive force between these particles for distances ranging from 1 micrometer to 100 micrometers, and then we generate 1,000 data points. Alright, so let's talk about the MATLAB code here. First thing that I did was clear my memory, which is what I normally do. I then define the charge of an electron. I define the individual charges Q1 and Q2. So this right here is really the delta D. It's defined as 1 micrometer, and we'll use that to increment our loop. And then we have our Coulomb's constant right here. So what I did was I created a loop which will essentially increment the distance here, dk, from 1 micrometer to 100 micrometers. And then I simply use this equation here, the same that is shown above, in order to calculate the force between them. And I reference that to an array with an index of k, and then I plot that value down here. And so, as one would expect, the positive attractive force, so the y-axis is the force and the x-axis is the distance, that grows drastically as the two charges approach one another and get closer, and then as they get further away, that value drops off. So a nice little MATLAB example for those of you who are interested to take a look at. And I think I've said this several times before, MATLAB is an integral part of this class, as well as, in my opinion, electrical engineering, studying electrical engineering overall. Alright, so now let's talk about current. In electric circuits, in this class, we really don't talk about charge as much as we talk about current, because normally work is going to be performed by the movement of charge, by current. So we talked about an ampere previously. What was that referring to? The ampere is the unit for electric current, or the rate of change of charge with respect to time. And so we have two equations here. We see here, right, is that charge is equal to delta Q with respect to delta T, change in charge with respect to time. We can also define it as coulombs per second, the number of coulombs that pass through a cross-sectional area per second. The direction of current is defined with the assumption of positive moving charge. We know this is not true because electrons are actually negative, but that's the convention that we use. So in that case, what we see is we visualize the flow of current as positive charges that flow from the positive to the negatively charged areas of electric fields. Okay, right, when we have, let's say, a resistor, and then we have the positive and negative charged ends, we imagine current flowing in that direction because we imagine it as the flow of a positively charged particle. All right, energy. So energy is a quantitative property that must be transferred to a body to perform work or generate lost heat. The law of conservation of energy states that energy can change forms but cannot be created or destroyed. Common forms of energy include kinetic energy, so that's that of a moving object, potential energy, which can be stored in an object's position within a force field, so for example gravity. Note that we could consider a coiled spring as a type of force field. So the position or the level of contraction of that spring would also represent an object position. Obviously, the position of an electron within an electric field would also be one that could create a potential energy storage. We have chemical energy, which is stored in the bonds of chemical reactions and released through reactions like burning. We have thermal energy, which is reflected by an object's temperature or average movement of the molecules within it. Again, thermal energy and temperature is really an emergent phenomenon because it only is quantifiable on larger scales. So the unit of energy is the joule, as defined below. It represents the total amount of work done by a force of 1 Newton acting through a distance of 1 meter. So here we have unit of energy is the joule, and the unit for that is kilogram meter squared per second squared. Okay, the total amount of work done by a force of 1 Newton. Work is energy transferred to or from an object via the application of a force along a displacement. In more practical terms, it represents energy transfer to do practical work, to perform some task, which works against the arrow of entropy. Remember, going back to that discussion of entropy before. We don't need to use energy in order to make the system more disordered, right? Your room is gonna get messy even if you don't do anything to it. Okay, just by the natural forces of nature. However, in order to work against that direction of entropy, to move from high to lower entropy on a localized scale, that is going to require some work to be performed. Power is the rate of energy transfer or energy transferred per unit of time. We'll discuss electrical power specifically in greater detail below. The unit of power is the watt, which represents 1 joule per second of energy transfer. We can also refer to power as the change, the delta work with respect to time, or force times velocity. And then work, right, we can calculate, and this is sort of the opposite of the expression above, right, we can calculate as the integral of power with respect to time. So, in essence, right, the relationship between power and work is described by derivatives and integrals. Work is the cumulative definition of power being applied over time. Force is an influence that can change the motion of an object. For example, it can cause an object with no mass with mass to change its velocity vector. Right? The simplest example of a force is you simply walking up to, let's say, a bowling ball and pushing it, right? Because that causes that object to accelerate in a given direction, and that acceleration is a result of the force being applied to it, which in turn requires your muscles to do some work. The unit of force is the Newton, which is equivalent to kilogram meters per second squared, and force, probably most of you remember this from your physics class, is equal to mass times acceleration. I mean, that's just one definition of a force, but we'll start off with that. Again, right, if we talk about the bowling ball example, it requires, let's say you apply the same amount of force. You apply that force to a bowling ball, you apply it to a tennis ball. The tennis ball is going to accelerate more because its mass is smaller as compared to the bowling ball, which will accelerate less. All right, so now let's talk about electromotive forces, which we are often going to use synonymously with a voltage source. So one type of force is the electromotive force, or EMF. Certain devices, such as batteries, can generate an EMF and move electrons against their natural flow from the positive terminal to the negative one. So you can think of this as like lifting a bowling ball from the ground to the top of a ladder, right? An EMF does the same thing for an electron. It moves it from where it wants to be. So if we're talking about a negative electric charge, it moves it away from the positive area of the electric field towards the negative. The EMF force transferred energy as work to overcome the repulsive force between the like charges, or overcome the attraction between the opposite charges. And so actually here, I think I used that same example. We can think, the one that I just said, we can think of the electron and EMF as a bowling ball and an elevator, right? The only way we can lift a bowling ball against the force of gravity is by using an elevator or something similar to perform work and lift that ball. Similarly, the only way we can move our electron against the electromagnetic force is by using an EMF to perform work and push that electron in the opposite direction that it wants to flow. Devices that generate EMFs include electrochemical cells like batteries, thermoelectric cells such as thermocouples, amplifiers and power electronic devices can also generate regulated EMFs, although they require some energy source. So we can take a look at this example. We see here that, and we're assuming this is a positively charged particle. So if you have a positively charged particle, it naturally wants to flow from the positive to the negative terminal of any device. Over here we see, right, it flows in this direction. The EMF is special because through applying work and drawing energy from another source, it's able to move the positively charged particle towards the positive terminal of the EMF. So kind of similar to an elevator, in the way that we can visualize it, at least, not in the way that it works, obviously. All right. So, like I said, we'll mostly for this course be referring to EMFs as voltage or sometimes current sources. And those two terms are somewhat synonymous, although they do have different connotations. All right, I would like to return a little bit to the topic of electric power. Electrical energy and power are observed from the movement of charged particles. It's quantified by the current, the rate of charge flow, across a voltage potential. Now the voltage potential, I should say, provides a barrier to this flow. It takes a lot of energy to lift 10 bowling balls per minute by a height of 100 feet. It takes less energy to lift 1 bowling ball per minute by a height of 1 foot. And we can expand that idea to electrical power, where the number of bowling balls moving per minute, that would be analogous to the current, right? I would be the number of bowling balls moving per minute. And voltage would be analogous to the height over which they are moved. So we can see here that it takes a lot more energy to move the same number of bowling balls, so let's say current stays the same, if our voltage increases, or the height, if we're going back to the bowling ball example, the height increases. Electric potential is the work or energy required to move an electric charge from one reference point to another within an electric field. Depending on which direction we travel, the system may need energy input or may generate energy output. Again, think about the lifting and the dropping of a bowling ball. If we want to lift, and I know this analogy perhaps is getting a little bit tired, but it's a really good one. Again, if we want to lift the bowling ball from the ground to the height of, let's say, 10 feet, we are going to have to apply some work. We are going to have to utilize energy to do work. However, if the ball is already 10 feet in the air and we simply let nature do its thing, it's going to hit the ground and release energy through vibrations and heat and all different forms. We see the same thing for a charged particle in an electric field. So a positive charge, I'm reading right here, a positive charge will naturally flow to the negative charge, releasing energy kinetically from the converted potential energy. All right, so this will flow here and will release energy along the way. It's this mechanism that we use to drive most of our electric devices. An EMF, an applied force, would be needed then to move our charge back to a non-rest position over here. So you can see here the back and forth between the EMF, which is constantly trying to inject energy into the system and move the particles against that natural flow, and then our loads, which for the most part will be extracting energy from that natural movement of the electrons. And so here we can see the natural flow of current for a non-EMF, non-electromotive force. And essentially, right, your positive charge will require some applied energy to flow from the negative to the positive terminal, and no energy to flow from the positive to the negative terminal. I think I said that wrong. It requires energy to flow from the negative to the positive terminal, and requires no energy to flow from the positive to the negative terminal. Quick spoiler, we call this the passive sign convention. This relationship of the voltage polarity and the current direction. All right, but we really haven't talked about what voltage and current are yet. Voltage represents the difference in electric potential between 2 points. Remember that potential is different at a different spot within our electric field. If we go back up here, let me clear this picture up a little bit. What we would see is that the electric potential at this point would be different from the electrical potential at this point, which would be different from the electrical potential at this point. The difference between the potential at two spots is what we call our voltage differential. Generally, we talk about voltage with respect to some assumed reference or assumed ground value. Current represents the flow of electrons along a path. We've already talked about this. And then resistance is another piece of this puzzle, which we'll talk about later. Essentially, resistance, as the name suggests, is a value which describes the amount which a material resists the flow of current. So if there's no electrical connection between 2 points, it would have an infinite resistance. It completely resists the flow of current. We've talked about electric power previously, although there are some equations that I would like to add here. We know already that the unit of power is the watt, which is a joule per second of transfer. Again, this goes back to the relationship of power being delta energy with respect to time, or delta work with respect to time. The new equation that I want to touch upon is this one here, which is an electrical version of the equation above. So we know that power equals force times velocity. We can also think of it in terms of voltage times current. Now I should note that for AC systems, there's a form of this equation, S equals VI conjugate. I'm not going to talk about that right now. Let's just assume a DC system, a simple DC system. So the amount of power that is released by some component, okay, or absorbed by it, is going to be defined by the voltage potential across it, as well as the current flowing through it. Higher voltage, less current, could absorb or inject the same amount of power as vice versa. Higher current, less voltage. So some online resources, some textbooks use an example similar to this right here, which draws an analogy between mass, or sort of pumping water, and electricity. I don't think it's necessarily the most helpful, but I drew this little picture to kind of illustrate. I'm not going to talk about it in too much detail, but if you want to, I mean, you can download the notes and take a look at it yourself. There's also tons of really great resources that use this analogy online. Anyway, what it does is it draws this analogy between some mass of water, or some generic mass, starting off at its rest state, which if we're talking about a gravitational field would be the ground, and if we're talking about an electric field, that would be whatever the minimum energy state is, whatever the most attractive point is. Then we use some sort of a force in order to lift, if we're talking about the mass example, to lift the mass from the ground. If we're talking about the electrical example, we would use an EMF, an electromotive force, to move it. And the result would be a change in its height for the mass example, and its electric potential if we're talking about the electric example. The result is that at this state here, the mass or the charge has increased potential energy, which then can be converted back to kinetic or electrical energy when it's released and allowed to return to its natural state. Velocity and current are somewhat analogous to one another, although not really, because current is number of units per second and velocity is meters per second. Currents always travel at the same speed. Essentially, the yellow lines here represent the curvature of space as a gravitational field, or they could represent the field lines of an electric field. And, we have work that's required to move a positive charge from its attractive point upward. Like I said, I'm not going to spend too much time on this example. You can take a look at it yourself if you're really interested, and try to draw whatever analogies you can from there. And plus, we sort of referred to this at other points in the lecture as well. All right, I think the last couple things I want to talk about here, this is really not electromagnetism specific, but the idea of units, which obviously is going to become increasingly important as we talk more about physical quantities, joules, newtons, volts, amps, etc. So we're, like pretty much any field of engineering, going to use the International System of Units, the SI. This is the modern form of the metric system, and it employs several fundamental units: length in meters, mass in kilograms, time in seconds, electric current in amps, temperature in Kelvin, quantity of a substance in moles, luminous intensity in candela. Now, other units do exist, but those are referred to as derived units. So voltage is a derived unit. Oh, so here's some examples. Frequency in hertz, that's 1 per second, or the inverse reciprocal of a second. Power in watts is kilogram meter squared over seconds cubed. Potential in volts, kilogram meter squared over seconds cubed amps. Anyway, this I'm not going to focus on too much because we're going to introduce units along with values, as we pretty much have done already, right? Amps is the unit for current, volts is the unit for voltage, watts for power, etc. I do want to talk about the prefixes though, because the prefixes are pretty important. I think most of you are probably already familiar with these if you have any sort of science or engineering background, right? We know essentially on the right hand side we have things getting smaller, and then on the left hand side we have things getting bigger. So down here is sort of like the starting point. So if you have 1 meter, you can branch off as things get smaller and go into centimeters, millimeters, micrometers, nanometers, picometers, femtometers, and all of those are defined by this coefficient here. Then, as we can start off with let's not use meters, let's use kilogram. We start off with 1 kilogram and things get bigger. So we don't really use decagram too much, but kilogram, we don't really use these for grams. Let's use volts. Okay, so we have kilovolt, megavolt, gigavolt, teravolt, petavolt, and the values, the coefficients that would be applied are shown right there. Now, I should highlight, I think I said this once before, that it's important we track units in our calculations. If the units generated by a calculation don't match the desired value, let's say we're trying to calculate power, but we don't end up with a unit of watts or something that's equivalent, then we know that we may have made a mistake somewhere along the line. So if we take a look at what's going on right here, this seems pretty obvious that it's a power value since it's voltage times, well, actually no, it's power squared. I think that's energy, but let's just use a generic X for the moment. So we multiply a voltage value by a current value. This right here is equal to 3 times 10 to the negative 3 volts, right, because it's milli. This is 4 times 10 to the negative 6 amps. And right here in this portion of the calculation, I'm not going to go through every step. I encourage you to take a look at it on your own. You can see how we account for those prefixes. And as a result, demonstrate that our output will be in volt amps or nanovolt amps, which we can represent as nanowatts. So this is one piece of the lecture where I think you really have to take a look at it yourself and practice on your own. I encourage you, whenever you're doing a problem, to take the units into consideration. Finally, we have one last homework that I am going to spend just a second going over. I asked the students to calculate a solution with the consideration of units for I squared R. Now I know we haven't talked about what resistance is yet, but this essentially is going to calculate power. I squared times the resistance. So this, if we talk about some element that has a given resistance and a current passing through it, the power being dissipated by that element is I squared R. Okay, so our I value is 20 milliamps and our resistance is 100 ohms. What is the unit of the output? What kind of calculation is this? And I tell you that, because we haven't talked about resistance yet, that ohms is equal to joule second per coulomb squared. All right, so what do we have here? And I use X again because we don't know exactly what the output value is. 20 milliamps squared times 100 ohms. I know that, so the first thing I do is I pull the actual numbers over here and I move the units to the right. So what we have is, we know that 1 amp is equal to, or proportional to, 1,000 milliamps. So what we're doing is we're using this to convert from milliamps to amps. Milliamps cancel out with milliamps. This is a conversion factor. This is our original unit. Then we multiply that by ohms. Okay, we replace ohms with joule second per coulomb squared. I also replace amp with coulombs per second, but since this is squared, it's coulomb squared divided by second squared. And then you can see here, this cancels out with this. This cancels out with the exponent, leaving us with joules per second, which is the same as watts. And this makes sense because we are calculating a power value, as I said before. So this is a nice example of how we can use our units to essentially verify our answer. I mean, it doesn't guarantee that our answer is correct, right? We could always have made a mistake with the numerical calculations, but at least it provides us some confidence that there's certain types of mistakes that we haven't made. And as we see right here, you simply apply the same numerical arithmetic processes, calculations, manipulations to the units as you do to the actual values.